So one of the first things you should always do on an AP problem are to ask yourself what models apply. And then once you've picked out models that you think apply, to start drawing diagrams that are relevant to that model. And so I'm going to record a series of videos where I summarize what are the key tools that are part of each model's toolkit. And this first one is on the constant acceleration of a particle model, or CAPM. Now the first representation that we used for the constant acceleration of a particle model was motion maps, where we have these dots that are essentially snapshots of where an object is at moments in time. And so it's like if every 1 second you made a mark that shows where your object is. And so when these dots are farther apart, it means the object traveled farther in that 1 second, so it's moving faster. When these dots get closer together, it means the object didn't travel as far in that 1 second, and so the object's moving slower. We also did a little bit of adding acceleration arrows to these motion maps, where the acceleration is how much the velocity is changing in 1 second. And so in this case, my acceleration is always acting to the left. Because this object initially slows down, the acceleration is initially in the opposite direction of the motion, and then when it speeds up, that's because the acceleration's in the same direction of the motion. And because we're on the constant acceleration of a particle model, I tried to draw these acceleration arrows all about the same size to show that that acceleration is constant. And then, arguably the most important representation that we used was VT graphs, where in this case, my object started with a large positive velocity, which means I have to start with a large positive intercept. That velocity would get smaller and smaller until it reaches a velocity of 0. And then to show it reversing direction on the motion map, the arrows go the other way. On a VT graph, I have to go from a positive velocity to a negative velocity. We also spent some time annotating these graphs, where we mark up things on the graph that have physical meaning. So for example, how far up or down this axis I go is my change in velocity. I can also annotate key velocities. The velocity that goes with this point at the end of the graph is my final velocity. The velocity that goes with this point at the start of the graph is my initial velocity. And then just like reading across the vertical axis gives me velocity, reading across the horizontal axis gives me how much time has passed. We also developed this idea that the slope equals the acceleration, and the area of this graph. I'm going to call this delta x1, and I'm going to call this delta x2. The area of that graph represents how far the object traveled. In this case, I split it into how far it travels one way, how far it travels the other. Now, we also used these VT graphs to build equations. We said that slope is rise over run, where the slope represents the acceleration, the rise represents the change in velocity, and the run represents the time. We also used the area to set up equations. In this case, if I wanted to find that delta x1, So how far my object travels in that first chunk of the graph. I've got a triangle, which means I need to do base times height divided by 2. The base of that triangle is how much time passes from here to here, which I labeled T1. And then the height of the graph is how far I have to go along the vertical axis from here up to here. So the height of this triangle. The way I drew this, that's V0. And then if I had numbers, I could plug those in to solve for these quantities. We also made some use of position versus time graphs, where the slope of your position versus time graph is your velocity. In this case, since the velocity is changing, the slope has to change. So I have to start out with a large positive slope, and I have to go towards a slope of 0. So like right here would be my slope of 0. And then my slope has to become negative and go to bigger and bigger values. So I end up with a parabola like that, where this would be what I labeled T1 on my VT graph. And then the vertical on this graph tells me about how far I traveled. So that would be my delta x1. The area of a position time graph doesn't really tell us anything useful, so it's mainly the slope that we're going to use. And then we also did just a little bit with acceleration time graphs, where acceleration is the slope of the velocity time graph. In this case, the way I drew my graph, my velocity time graph has a constant negative slope. So that means I have a constant negative acceleration. And it's going to be very unlikely that you will, for this course, have to deal with changing accelerations. And then the area of this graph is the change in velocity. And again, how far across I go is the time. And then on this graph, I'm not going to put a, sorry about that, I'm not going to put a delta A because the acceleration's constant. I'm just going to put that acceleration has this constant value. So those are the major diagrams that we used for constant acceleration of a particle model. And we built most of our equations from these graphs. But I do want to remind you that as an alternative, there are 3 equations at the top of your formula sheet. They look like this, where that you get to the same place as you could with the equations from the graphs. Now these do use a lot of subscripts. So first up, whenever they have this x subscript, that's just used to indicate the direction. When you're dealing with something that has vertical motion, it might make sense to change that subscript to a y. But anywhere you see that little x subscript, that just tells you it's referring to the x direction, so horizontal motion. And then a few of these have a 0 subscript. That is indicating the time. So there's all my 0 subscripts. And in fact, it's indicating a time of 0, which means it's talking about the initial value. And so when you have v with, oh, I'm misspelling. So when you have a v with a little 0 after it, that means you're talking about initial velocity. When you have an x with a little 0 after it, it means you're talking about initial position. So you can get to the math from either these equations or from the slope and area of the graphs But keep in mind that regardless of how you get the equations, being able to read and interpret these diagrams is going to be key on the AP exam.